This is your module 3, which defines a small signal amplifier. So in that, the first subunit of module 3, AC load line and amplification, will be discussed in this presentation. Objective of a small signal amplifier: to make you familiarize with the RE model and pi model, which are the various models which are useful for doing the analysis and small analysis in DC domain for small signal amplifier. Use of an equivalent model to find the important AC parameter of an amplifier. Understand the effect of load resistance and source resistance on the overall gain and characteristics of amplifier. To get you aware of the AC characteristics of a CE amplifier and develop a skill in troubleshooting of the amplifier network. Contains, we will get an introduction to what is an AC amplifier, then amplification in AC domain, what is the role of DC network in amplifier, analysis of the network based on the models, then how do we model our given network, out of the various configurations that you have come across, that is common emitter, common base and common collector. Out of that, you are using your common emitter configuration, and in common emitter configuration we are using two biasing, that is common emitter bias and common emitter voltage divider bias. Introduction. So in past you had seen the DC analysis of the electronic device, and in present case we'll be dealing with the AC analysis. Major concern in handling AC device is the magnitude of the input signal. So depending on the amplifier, they are broadly classified into small signal and large signal amplifiers. Then three models largely used for analysis of the network are the RE model, hybrid pi model and hybrid equivalent model. RE model is most popularly used because of its real-time analysis. So amplification in AC domain. What is meant by amplification in AC domain? The amplification process, output signal is greater than the input signal. The output AC power is greater than the input power. How does this output power grow or increase? According to the universal law, conservation of energy dictates the total output power of the system. The power of an output system cannot be greater than the input power. This is true in amplifier because the DC power is contributed by the DC source present in the amplifier system, irrespective of some amount of power is lost in dissipation by the device and resistive component. So there is an exchange of DC power to the AC domain that permits higher AC power in the output. Understanding the role of a DC network in an AC amplifier. So without the control mechanism, here the simple network is given with a resistance and a DC source. So what it is doing is that this, when we are activating this simple resistive network with this DC source, you will get a current pattern which is uniform with respect to time. So that is what is shown over here without control mechanism. Now if we are using a control mechanism, here this resistive component is replaced by an active component. It can be a diode BJT, FET, E-MOSFET or ahead. And this resistance is used for a current control through this active device. What we do is a small current, which is an activating current, is used for activation of this network of this particular device, and this leads to oscillations and generates a continuous time signal in time domain. So you can say that the current small in the current mechanism is going to control your output AC signal. So total current is the current flown due to this DC source plus the current which is generated, AC current that is generated by the current mechanism. Now one thing we have to remember, that if the peak value of this DC current that is generated by the DC source exceeds the limit, there will be clipping in the output signal, which is an undesirable factor as it leads to distortion. So we have to take control of this DC source. Analysis of the network. So while doing the analysis of the network, we will be using the superposition theorem, which helps in separation of the DC and AC component, permitting the separation of DC and AC response of the system. A network is analyzed in two steps: perform a complete DC analysis, perform a complete AC analysis. Then modeling. Modeling is nothing but having an idea of a network and then performing the analysis on it and then putting it in a real-time operation. So modeling is nothing but expression of your idea of a network on the sheet or on the paper. So model is a combination of a circuit element properly chosen that best approximates the actual behavior of a semiconductor device under specific operating conditions. Then BJT transistor modeling. In the very brief introduction, I talked about the various models that are used for analysis of bipolar junction transistor. So hybrid equivalent network. This is a very convenient network wherein all the parameters can be collected from the data sheet, arranged, and then analysis is done. In RE model, the parameters are determined at the actual operating condition. RE model failed to include a feedback term. In some cases, it may be important. There are some pros and cons when we are designing the models. So RE model is really a reduced version of an hybrid pi model used almost exclusively for high frequency analysis. Demonstration of an hybrid pi model. Step 1. Consider the given network, the network that is given to you. Then try to find out which type of biasing it is used. Now the present network that is given here is using a voltage divider network. So it is a voltage divider biasing, common emitter biasing. Then what you do is, while doing the DC analysis, you short circuit the capacitors and the DC source, perform the DC analysis. Once the DC level can be once the DC level or the Q point is set, that can be ignored and perform the AC analysis, right? The very important rule is that all the coupling capacitors provide open circuit and inductors short circuit for AC analysis. So C1 and C2 are the coupling capacitors and C3 is a bypass capacitor. So even this will be shorted. Draw the equivalent circuit. So we have drawn here, we can see that the DC sources are shorted and capacitors are also shorted. This was a bypass capacitor across RE, so the component is also shorted. Defining the important parameters. Important parameters when you are doing the AC analysis are the input impedance, output impedance, and the voltage gain, overall voltage gain of the given system. So this is a single stage amplifier what we are talking about. So when you are giving an input signal, input voltage signal, you'll be able to generate, circuit will be able to generate an input current, and we will be able to measure the output voltage with output current. Now here one thing we have to remember is that the polarity of the voltage is positive, so current is flowing out of the output port. Then impedance, input impedance and output impedance. All things what I've talked about are explained in the points given below. I'm reading out the points. Input and output current are entering inside the system. Zi is the input impedance looking into the system. Z0 is the output impedance looking back into the system. If I0 is defined in opposite direction to the one given in figure A, the polarities of V0 should be opposite. So redraw the circuit for AC analysis. While redrawing, what we have done that all the capacitors are short circuited here, as well as DC sources are also short circuited. Now this particular network is ready for the use of AC analysis. So we have refined our network. Summary of step for obtaining an AC equivalent circuit. Set all DC sources to 0. Replace them by a short circuit equivalent. Replace all capacitors by short circuit equivalent. Remove all elements bypassed by a short circuit equivalent introduced by step 1 and 2. Redraw the network in a more convenient and logical form. Common emitter configuration. This is your input terminal, common emitter configuration, an ideal case wherein we are applying a base to emitter voltage and we are obtaining the base current and the output current, that is IE in this particular network. So you draw an AC equivalent of this RE model. So RE is the resistance present between the base and the emitter terminal, and between the collector and the emitter terminal is the current source beta IB. So input impedance Zi is the ratio of voltage across RE into the current flowing into the terminal. So VBE upon IB is the input impedance. Defining VBE is IE into RE. So at this particular node, if you focus, IE is the sum of IB and beta IB. So when you sum them, you get this relation IC plus IB into RE. After that, what you do is substitute the value of IC, which is equal to beta times IB. So you get a refined equation of a current, that is beta plus 1 into IB. So VBE is equal to beta plus 1 into IBRE. Zi is equal to VBE upon IB. So your input impedance is approximately equal to beta times RE. Now what is this beta? Beta is the DC current gain. And how do we define our parameter RE? Re is equal to 26 millivolts upon the emitter current, upon the emitter current. So in some cases this IE is equal to IC. So RE will be given by 26 millivolts upon IC in that case. Early effect. In this slide, we are trying to understand the effect of operating point Q on the network. So you can see that this is a fixed voltage VA, and VCEQ is the operating point voltage, and ICQ is the operating point current. So when your operating point is moving from active region to either saturation or cut off due to instability in the circuit, then you will find that the output impedance is also rising or increasing with the increase in collector current and the collector to emitter voltage. So this effect is called as an early effect. Now here defining, as the base current increase, slope of the line increase. Slope means which is defining the resistance, resulting in an output impedance with increase in base and collector current. This is defined as early effect. So R0 is equal to the differential change in the voltage to the differential change in the current. So VA plus VCEQ upon ICQ. So R0 is a differential change. R0 is the ratio of the differential change in collector to emitter voltage to collector current. Hybrid pi model of common emitter configuration. This we will be frequently using, so go through it very properly. On the input side it is beta Re, output side between the collector to emitter is a current source beta IV along with the resistance R0. So R0 has to be defined in a problem if any analysis is to be done. Re we can find out. So common emitter bias, this is a simple circuit. This is a DC equivalent circuit of the common emitter configuration and AC equivalent circuit. This is RE. Okay. What we have done is, all these capacitors which are there, these are short circuited. You can see from here. This should be RB, I guess. Base resistance, RB. So this is your collector terminal. Current is IC. So I0 is equal to IC in this case. So doing the AC analysis, Zi is equal to beta times Re. RB is very greater than 10 times RE. So input impedance ZI is equal to beta times RE ohms. To find out the output impedance Z0, the current source is open circuited. Going to the previous slide, at the output terminal, there was a current source right here, which was beta IB in parallel with R0 and RC. So this is your R0, this is your RC, and from here you are finding out the impedance Z0. So this will be open circuit. Fine. So that is why you get Z0 is equal to R0 parallel RC. So R0 we consider to be 10 times RC. So definitely Z0 will again refine to here RC. So simple example here, determine RE input impedance when R0 is infinity, Z0 AV, Z0 is output impedance, AV is the current gain when the output impedance is that is R0 is infinite. So beta times RE, first you check how much it is, then define your values here. RE is nothing but capital RE, small, same thing. So ZI comes out to be 1.07 kilo ohms, Z0 is equal to RC, and AV is minus RC by RE, so it is minus 280.11. A voltage divider bias. So first perform the DC analysis. When you are performing the DC analysis, these capacitors will be again short circuited. Now here you will find a new component, that is bypass capacitor CE. So this will be also short circuited. So this component will be replaced by a short circuit. Short circuit. So DC analysis. Here this circuit is given. So we are redrawing the DC analysis for DC analysis. This circuit is redrawn, and based on that, here you apply a voltage divider rule, or you apply an approximate rule and break down this voltage this into R1 R2, a parallel combination. So R dash is R1 R2 upon R1 plus R2. From the original voltage divider network, input impedance ZI is R dash parallel beta times RE. So your RE is equal to 26 millivolts upon IC. As I told you, in some cases IE is replaced by IC. Next, AC analysis of voltage divider bias. So here you replace that active component by beta RE into current source. Now since emitter is grounded, this is placed at an ground condition. So between collector and emitter is your load resistance RC, along with R0, and on the input side the two dividing network R1 and R2 are present. So R1 parallel R2. This defines R dash. So with Vi equal to 0 and Ib equal to 0 and beta Ib equal to 0, Z0 is equal to Rc parallel R0. How this happens, that we'll see. This is your input terminal. So here this Vi is 0. So no current flow in the input terminal. This is your input network. Coming to the output network now. This current source is open. So we are left only with R0 and Rc. So your output impedance is Rc parallel R0, Rc parallel R0. So if R0 is greater than 10 times Rc, so Z0 will be equal to Rc. Next slide shows you how to measure a voltage gain. So voltage gain is defined as AV because Rc and R0 are in parallel. So the voltage across this Rc and R0 will be minus beta times Ib. This is beta times Ib into parallel combination of R0 and Rc. Ib is Vi upon beta Re. Vi is the potential across this here. So current is nothing but voltage divided by resistance. So Vi upon beta Re. So substituting Ib and V0 relation in this equation, beta times Vi upon beta times Re into Rc parallel R0. So V0 is equal to minus Vi upon Re because this will cancel out. So Rc parallel R0. So that is why your AV is equal to minus Rc parallel R0 upon Re. Again refine your relation of the voltage gain. Taking R0 to be greater than 10 times Rc, AV is equal to V0 upon Vi, which is minus Rc upon Re. So negative sign shows that there is a phase relation between the input signal and the output signal of 180 degree. Suppose your input signal, what I draw here like this. So output signal will be phase reversed. This should be 90 degrees, sorry. Not 180. Fine. Numerical for the network shown in figure, define resistance Re, input impedance, output impedance when R0 is infinite, voltage gain when R0 is infinite, and compare the value when R0 is 50 ohms. Okay. So go for DC analysis. First check where beta times Re is greater than 10 times R2. It is satisfied over here. So proceed to do the DC analysis. Using the approximate approach, this is the first step. Step 1, get the voltage VB over here, which is a relation of R2 upon R1 plus R2. This is R2. This is your R1. RC, and this is your RE. So VB is equal to 2.81 volts. VE is this is VB. This is your VE. Voltage existing between the base to emitter is VBE. So VE is equal to VB minus VBE. Right, simple relation. VBE is equal to VB plus VE. So this particular equation will come into picture. VE is equal to VB minus VE. So this will give you 2.11 volts. Next step is we are going to do the AC analysis of this circuit. So first find out the input impedance here. Input impedance is a combination of R dash into RE, beta RE. So DC current gain is given. RE you found out, that is 26 millivolts upon the collector current that was flowing. So this comes out to be 1.733 ohms. Next, find out the output impedance Z0, that is approximately equal to RC, which is 6.8 volts, and voltage gain is RC by RE, which is minus 368.76 volts. Input impedance when R0 was given to be 50 ohms, that time it has come out to be 68 kilo ohms. So AV, how much it is? RC by R0 into RE. So this is 324.3 volts, which shows that when R0 was infinite, that time the voltage gain was this much. And but when R0 is 50 ohms, that time it comes out to be when R0 is equal to 50k, voltage gain is 324.3, of course with a negative value. And when R0 is infinite, that time it is minus 368.76. So we can, what is the conclusion is that when we are including some resistive part in it, voltage gain is reducing. Or when we are trying to apply some load to an amplifier, load, it can be a speaker in your public address system or a mic. So when you're applying a speaker, it offers some resistance, and which will try to reduce the gain of a system. So that time we have to take an alternative arrangement, is that we have to apply some amplifier to increase the amplitude of the signal in public address system. So there was a measurable difference in the result for Z0 and AV, because the condition that R0 is greater than RC was not satisfied. So common emitter biasing. Common emitter biasing has a resistance RB between the DC supply and the base terminal, and the collector resistance between the DC and the collector terminal. So you draw this circuit, redraw. Now here we have to see that the emitter resistance comes into picture. Okay. This particular terminal between the emitter and base, there is a component beta Re. Between the collector and the emitter, there is a current source beta IB. Here this is beta Re. Between base to emitter, between collector to emitter is current source beta IB. So here you can see a dynamic resistance Re is pictured over here. That means between the base and the emitter there exists a resistance Re. So that is why we replace it with beta Re here. Okay. So you find out the voltage Vi, Vi is equal to IB into beta Re plus IE into Re. Here voltage Vi is nothing but the sum of voltage Vi. Vi is the sum of beta times Re into IB plus IE into Re, where IE is equal to 1 plus beta times IB. Substitute this relation in this, you will get the complete input voltage. So in order to find out the input impedance ZB, it is nothing but Vi upon IB here. So beta times Re plus 1 plus beta times Re, capital Re. So this defines your input impedance ZB. So input impedance for an unbypassed Re, this is unbypassed Re. This much. Beta is normally much greater than 1, so approximate value of ZB is beta times Re plus beta times capital Re, or the unbypassed resistance Re. So we come to this relation, ZB is approximately equal to beta times Re into capital Re. Re is much greater than small Re, so this reduces your input impedance ZB is equal to beta times Re. So now we are in a position to find out the input impedance Zi. Zi is equal to RB parallel ZB. Output impedance Z0 is nothing but equal to RC, because this will be open circuit. This about the voltage gain now. So your input current IB, it is the ratio of VI upon ZB. So your ZB is beta times RE plus RE. So VB is I0, sorry, V0 output voltages, I0 into RC here, which is equal to minus beta times IB into RC. So substitute this, collect the term, substitute the value of the current I0, which is IB into VI upon ZB. So AV is V0 upon VI, which is equal to minus beta times RC upon ZB. Fine. So we have to define three parameters, that is input impedance ZI, output impedance Z0, and the current voltage gain AV. So what is ZI? ZI is RB parallel ZB. ZB is equal to beta times RE plus RE then output impedance is nothing but equal to RC. Output voltage gain is nothing but minus RC upon this whole thing are the base current IB, whole current I plus this. So it is RB parallel ZB. So in this way we perform our AC analysis. Fine. Here one thing we have to remember, that since the voltage gain is free from the factor beta DC, it is independent of the variation of beta, and relatively the circuit will remain stable. Negative sign shows that there is a phase relation between the input and output signal. So phase relation is of 90-degree phase relation. Suppose if I draw an input signal over here like this, the output signal will be of the reverse polarity like this. So this is termed as a phase relation. So phase relation exists between V0 and Vi. Negative sign indicates a phase relation. Okay. Next, we'll solve some problem based on this. So for the network common emitter unbypassed, determine the value of Re, small re, which is the dynamic resistance of the transistor, then input impedance, output impedance, and the voltage gain. Here R0 is not given. Yeah, R0 is given to be 40 kilo ohms and beta is given to be 120 ohms, 120. So based on this, you will have to solve the problem. First approach for DC analysis. So find out the current IB. So when you are drawing a DC circuit, here I am drawing it now. .30 volts. This is your collector terminal. RB. This is RC. This is your RE. Now this is been bypassed by an capacitor. Okay. So when performing DC analysis, this will be an open circuit, short circuit. Fine. So my actual circuit is like this. Okay. So IB is nothing but VC minus VBE. So VCC minus VB upon RB plus 1 plus beta times RE, because current flowing IE is IB into 1 plus beta. Fine. And RE is 26 millivolts upon IE. So this comes out to be this much value. So you have found out the value of RE from DC analysis. Now we have to go to AC analysis to define the input impedance, output impedance, and the voltage gain. Here circuit, original circuit, and the DC analysis circuit. Beta RE, beta IB is existing. So actually we are using an RE model. R0 is, first we check the condition. R0 is 10 times greater than RC plus RE. So if it is greater, then your condition is satisfied and you can perform an AC analysis. So ZB is nothing but a combination of beta times RE plus RE. So that comes out to be this much. Actual ZI is RB parallel ZB. Z0 is RC. Why? Because this current source is going to act as an open circuit. So when doing your finding out your input output impedance, your circuit will be like this. Z0. Okay, so Z0 is equal to RC. Now since R0 is greater than RC, your output voltage V0 is equal to beta times RC upon ZB. So it comes out to be 3.89. And if you are using RC upon RE, then it will come out to be minus 3.93 if R0 is not given.